Okay. Let's see. All right. Homework is coming this week. I went ahead and posted a message that can get you started preparing. So, our cookbook, this is your recommended spot for getting up to speed on R. I gave you some sections that you can be reading. What I'm going to do today is finish going through the notes that we were looking at last time. We're introducing multivariate statistics, what it's about, what are its common features, what are typical tasks. We talked about dimension reduction as one common task. We'll do statistical inference, like testing whether a mean vector is the same as another mean vector. We can do that in an ANOVA way, testing whether 3 or more mean vectors are different from each other. We can do that in a linear regression way. We can do multivariate linear regression where the response variable is itself a vector. Exploratory things, we saw, or at least we motivated the ideas of clustering and principal component analysis, which is a dimension reduction technique. And I was walking through some examples of what these things look like. We ended up here last time. So I wanted to say a few things about discriminant analysis and its related task of classification. So suppose we have multiple groups that our individuals can be classified into. Could be have cancer and not have cancer. Or it could be spam email, not spam email. Credit risk, not credit risk. Doesn't have to be just 2 classes. It could be 3, 4, 5, whatever. It might have tumor class. Do you have prostate cancer with Gleason score 1, 2, 3, 4, or 5? But the idea is that we have a categorical variable that we would like to make predictions for. So suppose we have data from individuals, and for each of the individuals, we know which class they are in. A simple example would be people with cancer, people without cancer. And for each person, we have some input variables. Maybe there are numerical variables. We have 10 people with cancer, 10 people without cancer, and for each person, we have multivariate data. So we might have, say, 5 biomarkers for each person. That might be a protein that's quantified. How abundant is this protein in your blood? Do that for 5 biomarkers, 5 proteins, you have multivariate data. Each person in our data set, each row in our Excel spreadsheet is a person. There's a column of the known class membership. Cancer, not cancer. Not cancer, not cancer, cancer. Column that tells us class membership. And there would be separate columns for each of the input variables, the predictor variables. So if we had 5 biomarkers, we'd have a column for cancer, not cancer, and 1 column for each of the biomarkers. In that setting, we can do what's called discriminant analysis. And that is the process of trying to find ways that separate the classes. In what ways, we have 5 biomarkers, multivariate data, in what ways, what patterns in those 5 numbers explain how the 2 classes are different? I said last time that often we'll be looking at taking a collection of input variables, p variables say, and boiling them down to linear combinations of those variables. We talked about principal components as linear combinations of your variables. You could take p variables, boil it down to a smaller dimensional space by doing cleverly constructed linear combinations of those variables. When we did canonical correlation analysis, I mentioned this last time, you have two sets of variables. Maybe you have 5 market volatility measures and 5 stock price increase measures or something. What's the relationship between these two sets of variables? The way we answered that was, again, try to carefully or cleverly construct linear combination in such a way that the correlation is highest. Discriminant analysis. We can do something kind of similar. We could consider what linear combinations of our 5 biomarkers. Suppose you took all 5 biomarkers for each of your people, and you did some linear combination of those 5 numbers. 2 times the first one, minus 1.4 times the second one, plus 0 times the third one, and so on. 5 numbers boil down to 1. Can you define a particular linear combination of the input variables that best separates the cancer from not cancer groups? Discriminant analysis is trying to find linear combinations of the input variables that are most informative in terms of separating out the classes. So we'll see this, discriminant analysis. It's a handy way when you have classification data like this to learn about and visualize what is the nature of the difference between the classes. The data set type that I described here, Excel spreadsheet with rows for each individual, a column for cancer, yes or no, and separate columns for input variables, that's called training data. In the sense that we can use these data to train or build a predictive method. If I know here's cancer, here's not cancer, here's cancer, here's not cancer, I can look for patterns in the 5 biomarkers that clarify which ones tend to be cancer, which ones tend to not be cancer. So we need training data. That's the first step of doing classification or prediction. You need data for which either a domain expert or through expensive assays or something, you figured out the actual answer. The hope is that you can avoid having to have the domain expert manually classify or use an expensive assay to classify. Once you have the training data, the hope is that you can build a model that you can use for the classification itself. So here's an example. These are genomics data where we have a sample size of 58. We have 58 people, 58 rows in our Excel spreadsheet, and we have 714 predictor variables. Each of these predictor variables is a numeric number that quantifies the abundance of a particular type of molecule in the human. For each of the 58 humans, half of them are healthy, half of them we know have cervical cancer, and we know which ones have the cancer and which ones don't. We have training data. Column full of cervical cancer, yes, no. 714 columns for these microRNA. All right, so we might want to build a predictive model. For each of these people, we have a genomic assay, and somebody has painstakingly diagnosed cancer or not. It would be very valuable if there was an assay that could be done in the clinic. Let's take a blood sample, say, from a person whose cancer status we don't know. Let's take a blood sample and run it through one of these genomic assays. If I could quantify all the microRNA for a person, then my model will make a prediction for me. Do your 714 numbers, does the profile of those look most like the training data with cancer or the training data without cancer? There's a bunch of different methods for doing that. How do you actually make a classification decision? We will learn about several different methods, starting with arguably the simplest, or one of the simplest, linear discriminant analysis. We'll talk about that more. But LDA, we'll see that. There's quadratic discriminant analysis, which is just like LDA, but it's a little bit more flexible. There's something called k-nearest neighbors. There's random forests, support vector machines, all kinds of sophisticated algorithms, all interested in doing this, classification. Let me say something here. When we do classification or prediction, we want, obviously, to be accurate in our predictions and classification calls. So consider an example where we have training data, and there are 8 plus 7 plus 3 plus 2, 20 people in our data set. Our training data has 20 observations. For each of the 20 observations, we have obtained the true assessment of their class membership. So let's say no, they don't have cancer, or C, they have cancer. There's 10 people in my training data that had cancer, that did not have cancer, and there's 10 people who did. On the horizontal, or on the side here, would be the claims that our model makes. Input the predictor variables and get back N or C. What's predicted by the model, what seems to be most likely. Whenever the truth is in, no, and we claim no, we claimed the correct thing. So this is good. There are 8 cases for which the truth was no, and we correctly predicted no. There are 7 cases where the truth is cancer, and we correctly predicted cancer. The things that are worrisome are in the off diagonals. So these 3 right here would be people who have cancer, but whom we predicted did not have cancer. So each of these was an error on our part. And similarly over here, these are people who did not have cancer, but we predicted they do. We would prefer not to make either type of error, but notice that these are different types. Would you rather have cancer and be told you don't, or not have cancer and be told you do? Probably don't want either of those, but you might argue that the first one is worse. If you have cancer, it's going to be bad if you don't know about it. So if this was our data, this array is called a confusion matrix. We'll see that more when we get to discriminant analysis. The diagonals are correct assessments. Off diagonals are incorrect assessments. So in our case, 15 out of 20 calls were correct ones. Our overall accuracy is 75%. We could also say our misclassification rate is 25%. One way to overall assess the performance of a classifier is just the overall accuracy. What proportion of your calls did you get correct? But there are other ways to assess accuracy. In particular, we could ask, among those who had cancer, what was our accuracy? That's called sensitivity. Sensitivity is the probability that you correctly classify as yes when the truth is yes. So the probability you discovered the cancer when it was really there. Specificity is the other type of error. That is the proportion or probability that a non-cancer person is incorrectly called cancer. Again, you don't want either of those to be big. Sometimes it's easier to control one than the other. Suppose we have a really rare disease, for example. One in 10,000 people have this particular disease. And we have a big data set with lots of people without the disease and just a handful of people with it. A classifier, a bona fide classifier, would be to say, give me your input numbers. I'm going to predict no every single time. I don't care what the numbers look like. I will always predict no. If that's your classifier, and there's only a handful of cases where the event actually happened, your overall accuracy is going to be really high, because almost never you make an error. But really, you're not doing anything useful. You're just saying no all the time. You would see that issue if you broke it down into sensitivity and specificity. Your specificity in that scenario would be wonderful, because you never incorrectly call cancer, but your sensitivity would be 0. And a biomarker or a classification method, in order for it to be worth anything, needs to have reasonable sensitivity and specificity. Okay, we will talk about cluster analysis. Cluster analysis is going to give us pictures like this that speak to how individuals or variables can be grouped together in natural clumpiness. When we make pictures like this, we're going to need to be able to say, how many, are there any clusters? Or is this just what I would expect to see by total random associations? So is there any real clustering? If there is, how many clusters are there? And what can we say about the nature of those clusters? If some individuals group together and these other ones group totally separately, what's the nature of that difference? Did this one have big variables for the first 3 and small ones for the last 2, and this one had the opposite, or what? Okay. So all of that was intended to mostly be preview for where we're going. Now let's start getting into the details. Okay? We need some notation because we are going to do some math. We're going to say our data can be represented as a matrix. If you had univariate data, like suppose we're just going to look at IQ of everybody in class, it's a univariate problem. One number for each person. You can represent your entire data set as a vector of, say, a vector of length 50. The first entry is your IQ. Second entry is your IQ, and so on. 50 numbers, a vector. Now that we're in multivariate world, though, each individual has not just one number, but p numbers. So instead of a vector of numbers for all of our n observations on one variable, we have a vector for the first variable and a vector for the second one, ... for the pth one. So we're going to say we have n items or individuals or trials, whatever it is that constitutes the individual assessments that we're doing or experiments, and we have p variables. That means capital X, our data matrix, is going to be n by p. And we'll use notation like x sub jk to indicate jth row, kth column. Or in other words, jth individual, kth variable. So that would be variable 1 in column 1. And row 1 would be item 1. So items or individuals in the rows, variables in the columns. Here's a data set that is on eCampus. Let me go ahead and open it up. So on eCampus, course content, data. I'm looking at the Pottery data set right now. This is a CSV file. I've also got a script. So this is just a text file. With a .r extension. Over here on my computer, I have the data right here. If I open this up, let's open it with Notepad++. When you are writing your R stuff, I think I mentioned this last time, I'll just reiterate. Please open a text file, save it as homework1.r or potteryanalysis.r, and put all your commands in there, together with comments like this one. So here's comments at the top of my R script. At the top of my R script, here's comments. I make comments by putting the numeric sign at the beginning of the line. And there's comments throughout, just to remind myself as I'm rereading through this what we were doing. And this also makes it easier whenever I hand it to you to know what I'm doing with the code. So these are the data we're going to play with. And we have 26 individuals. There's 27 lines in the file, but the first line are variable names. And these are, let's see, samples of pottery found at 4 different locations. So these are old pots that were dug up at archaeological digs. And each of the pots were assayed for the percent composition of 5 different metal oxides: aluminum, iron, magnesium, calcium, and sodium. So multivariate data, 26 individuals. Each individual has these variables. We also have, over in the last column, a categorical variable. Takes the values L, C, I, or A. So these would be indicating the kiln sites, the locations. Here, I'll show you this in the R script in just a second, but I'm going to pull out from those 26 just a really small example for us to do a little bit of calculation with. Here are the first 4 observations, and I'm only looking at 2 of the variables momentarily: calcium and sodium. Over here in the script, pottery.r, let me show you how we can do what I just did on the screen. Let's read in the data. To read in these data, I'm going to be giving you code that you can use to read in our data sets. In this case, you can use the read.delim function. And I want to copy this and go over to R, paste it, and run it. If I do that, or before I do that, I need to make sure that R is looking in the right directory. When you open R, it has a default location where it's looking on your hard drive. And if you try to say read.delim dataset.txt, if that file is not in that working directory, it'll throw an error. So I'm going to check where we are looking by typing git wd, git working directory. And Quan was good enough to go ahead and set us up in the right place. If I was not in the right place, then on a Windows computer, I would do File, Change Directory. On a Mac, I would do Miss, Change Directory. So you click those, it opens up an interface, and you just navigate to the right directory. Now that it's, well, actually this is not quite in the right place yet, but we're currently pointing to right here. And I want to point inside here. So I think what I will do is just say data /. I'm currently in the 636 folder. Inside that folder, there's multiple folders. One of them is called data, and inside data is pottery.txt. Let's see if this works for us. Okay, we have read in data. If you type ls, R will tell you all the objects that are currently available to you in this current workspace. We have one thing right now. If we were to create another variable, like here's x, a variable that is the vector of numbers from 1 to 10. X is an object. It's a vector of numeric values. When I say ls, there's two objects now in my R workspace. So DTA, that's my data set. How do you get started with a data set in R? First thing I would do is ask, what are the dimensions of the data? So DIM will tell us how many rows, how many columns. We have a two-dimensional array, so it's going to give us two numbers. The first dimension has 26 elements. The second dimension has 6 elements. R can do more than 2 dimensions in its array representation. We'll just look at 2-dimensional for this class. We're going to have n by p matrices. So I know the dimensions of my data. It's a pretty small data set, so I'll just type it and hit enter. If it was thousands of rows, typing it and hitting enter would not work well because it would just fill up the whole screen. Small data set, might as well just type it and look at it. Another way to look at your data that's better when you have larger data sets is you could use the head function, which shows basically like the head of the data, the top of the data, specifically the first 6 rows. So if you read in a data set and you just want to take a quick peek at it, head is good. There's also a tail function that shows you the last 6 rows. And what I would recommend is summary of the data. Summary gives us this. So it will, for each of the columns, give us some summary, some reasonable summary. If it's a numerical variable in the column, then it gives us a summary like this. It shows us the median, the mean, the 25th percentile, also called the first quartile, and the 75th percentile, also called the third quartile, in addition to maximum and minimum. All of the first 5 are numerical variables. The last variable is not. It's categorical. And R recognizes it's categorical. With a categorical variable, summary will be the tabulation, the frequencies with which each of the different categories showed up. So by doing the dimensions, taking a peek with head, and doing summary, you have a quick feel for the data. Okay, I'll show you some other examples as we go, but what we might see in this is there evidence of outliers? Is there evidence of missing values? Is there anything else unusual about these summaries that I need to look into further at this stage? All right. In the slides, I said, let's pull out just a really toy subset of the data. There's only 26 observations anyway, but here's the first 4 and 2 of the elements. All right, so let me talk about this right here. This is where the square bracket stuff, this is the kind of thing I recommend you go read our cookbook about. When you have an object in R, like x is a vector, the length of x is 10. And suppose we just wanted the 4th element of this. Give me the 4th element of the vector. You can do that using square brackets. Okay, so to subset a vector or an array, square brackets is one way to do it. So x4, the 4th element was indeed 4. What if I wanted let's say, the odd numbered elements. Give me the first element and the third one, 5th, 7, 9. The C means concatenate or string together. So put together these 5 numbers and then use those as indices to subset X. That's going to give me the first element, the third element, 5th, 7th, and 9th. What if I wanted everything but the 5th element? Give me all those numbers, but pull out the one that's in the 5th spot. You can do minus in front, and you can do minus concatenate. So everything but 2, 4, 6, 8, 10 will give me the odd numbers again. Oh yeah, sorry. Okay. If you have a vector, square brackets lets you pull out subsets. Suppose we have an array. I'm going to make a matrix. So give me some randomly generated numbers, 12 of them, and let's organize those numbers into a matrix with 4 rows and 3 columns. 4 by 3 matrix. Now, suppose I want the third row, third column. I just want to pull that out of this matrix, square brackets, but now it's a 2-dimensional array, and so I need to tell it which rows do I want and which columns do I want. If I want third row, third column, I can just do 3, 3. So there's third row, third column. Suppose I want the entire second column. I want to pull out all these 4 numbers right here. The way I can do that is to leave the first index blank. That means don't affect the rows at all. Leave them all in place, but only give me the second column. Those are the 4 numbers. And similarly, square brackets with a 2-dimensional array, which is the same thing as your data set that you've read in, you can do give me these rows, comma, give me these columns. So back in the script, I'm going to take the first 4 individuals, first 4 pots, and just the 4th and 5th columns. One, 2, 3, 4. I'm going to take calcium and sodium. Only the first 4 rows, just to play with it for a moment. So here is toy version of our data. And I'm going to save sample size currently as 4, because there's 4 rows. So this is the matrix from the notes right here. 2 variables, 4 items. Okay. All right, let me leave it at that. When we have data in, you can use summary to get quick summaries, look at missing values, outliers, and then you also want to compute some other statistics, summary statistics. The summary function showed us mean and median and range, but we could also manually compute the mean, and we might want to compute a measure of spread as well. So Stat 101, you learn that a random variable can be characterized in terms of both location, where does it tend to be, what's the average value, and spread. You could have 2 random variables with the exact same average, but they differ in spread. One's much more spread out than the other one. So in terms of characterizing the outcomes of a particular random process, mean or location and spread are important. And now that we're in multivariate world, we're also going to care a lot about co-relationships among the variables. If we were doing univariate statistics, we'd be pretty content with just a mean and a variance. But now that we have multiple variables, we're going to care about the mean and the variance of each of the variables, but also about the joint relationships between the variables. So you're familiar with the idea of correlation. Correlation is one way to assess association between two variables, between two numerical variables. It is a linear association that it's trying to gauge. Correlation between two variables, think of it like you're going to draw a scatter plot between them, fit the best fitting line to the scatter plot, and ask how closely does the scatter follow that line. If it's really tightly following a line, then the two variables are highly correlated. They could be following a positive slope line, in which case they're positively correlated, or they could be following a negatively sloped line, negative correlation. All right, a little bit more notation. We're going to be saying, remember, capital X is our data set, n by p matrix of numbers, unless we say otherwise. We're going to be thinking they're numbers. So let's compute averages and variances, sample averages and sample variances. In statistics, there is a population of interest, and in the population, there's an average and a variance. We call those parameter values. Those are fixed quantities that we wish we knew, but we can't because we don't have the whole population. So in practice, we have a sample, and we can compute the sample average and the sample variance. All right, so sample average for the kth variable, we're going to call it x bar sub k. And that is what you would think it would be, the sample average of all the observations for variable k. So xjk, if you let j go from 1 to n, that's going down the rows of the kth column. Add all those up and divide by n, sample average. Sample variance is defined almost exactly the same way as you would have seen it in Stat 101. It's, roughly speaking, an average of squared differences between observation and the mean for that variable. This looks like an average squared deviation between the data observations and their average. So if the data is really spread out, then on average, you're going to tend to have big discrepancies. Data tends to be far away from the mean. Will translate to a big variance. Whereas if all the points are piled in really close to the mean, all these squared deviations are going to be small, translates to a small variance. So variance is one of many ways for us to measure just how spread out things are. Another way to measure spread would just be what's the maximum minus the minimum. That's a number that measures spread. Interquartile range, the height of the box in the box plot, is another way to measure spread. We could do the average absolute difference between observation and sample mean. That's another way to do it. For mathematical reasons, a variance is pretty handy. Okay? So we tend to use variances in statistics. We're going to let sk squared indicate the sample variance for the variable k. We're also going to use s sub kk. The reason for that notation will become clearer soon. And one thing to comment on here, Stats 101, when you met sample variance, you saw a slightly different formula. So the Stat 101 sample variance is the same summation, sum over all the I to 1 to n, observed minus sample mean squared, sum all those up, but then divide by n minus 1. So here in our notes, we're dividing by n. It's technical reasons why you divide by n minus 1 instead of n. It turns out that a good estimate of the variance, called the maximum likelihood estimate, is this one, divide by n. But there's some technical reasons that have to do with operating characteristics of the estimate that say if you divide by n minus 1, it's a little better. It's unbiased. So don't worry about that too much. We will eventually switch to dividing by n minus 1 for part of the class. But in case you caught that and it made you wonder, I thought we divided by n minus 1. We are going to divide by n minus 1 eventually. So there's mean and there's variance, location and spread. I also said we're going to be interested in joint relationships or co-relationships between our input variables. So let's think about correlation and the related quantity covariance. Suppose we have p variables and pick 2 of them. So variable I and variable k. We have 5 variables. Let's look at the second one compared to the fourth one, say. The covariance, the sample covariance, we'll define a population covariance later, but the sample covariance, we'll say S sub I k. Remember that the sample variance is S sub k k. So S sub I k is an average, so add up n things and divide by n, and the things you're adding up are these products. So it's the x's for variable I minus the mean for variable I times the x's for variable k minus the mean for variable k. So if variable I and variable k tend to go together in a positive way, positively correlated, then whenever this quantity right here is positive, this quantity is also going to tend to be positive. And conversely, whenever this is negative, this will tend to be negative. In which case, this is going to tend to be positive, the product. So the covariance is going to be positive. If it's negative correlation, then when this one's big, this positive, this will tend to be negative, and vice versa, in which case the covariance is negative. Covariance is a measure of co-relationship. How do things change together? Covariance can be any number between minus infinity and infinity. If it's positive, then it's a positive relationship, positive linear relationship. If it's negative, it's a negative one. What we're more familiar with than covariance is correlation. So R sub I k is the sample correlation between variables I and k. And it's defined in terms of the covariance. The correlation between variables I and k equals the covariance between I and k divided by the product of the 2 individual standard deviations. So we have covariance, which is a number that can live between minus infinity and infinity, and its sign tells us about the nature of the linear association. And then we standardize it by dividing by the product of these standard deviations. What that does is it takes the numbers from minus infinity to infinity and it shoehorns them into between minus 1 and 1. So correlation is basically like a standardized version of covariance. It's a number between minus 1 and 1. The closer it is to 1, the tighter the nature of the positive linear relationship between the 2 variables. The closer it is to 0, the tighter the nature of the negative relationship. To minus 1. The closer it is to 0, the stronger, there is no evidence of linear association. Let me draw a picture real quick about this topic. Correlation. We have this data matrix n by p. So we're going to be talking about data like this throughout the semester, n by p. And what we're going to do with this is compute a matrix of sample variances and sample covariances. From that, we could get a p by p matrix of correlations. Ones down the diagonal correlations on the off diagonal. So don't worry too much about this yet. We're going to see lots more of this. But we're heading this direction. We want to talk about the variances of our variables, and then in the off diagonal pieces of this P by P matrix will be covariances. Capital S, and to a lesser extent capital R, they're going to constitute like all the information in our data. And much of what we're going to do, principal components, canonical correlation, several of these things are going to go to the covariance matrix and do matrix operations, linear algebra tricks on covariance matrices. Let's see, what was I going to say? Come back here. I was going to say something about correlation. Almost done. Suppose we have two variables, x1, or let's say xi and xj and xk. Suppose you draw a scatter plot of these two variables, and you see that. There is a line that we can kind of see behind the scenes that the points are following. The nature of that line is positive slope, and the dots are fairly closely following it, as opposed to, say, another picture that has the same line, but its points are more spread out. The picture on the left, even though they both have the same slope, the picture on the left is going to have a higher correlation. The strength of the linear association is stronger because the points follow it more closely. Here was the picture I wanted to make to speak about correlation being a linear association. That's something that doesn't always click initially when you are introduced to correlation, but when we talk about correlation and covariance, we're talking about linear associations. And in particular, suppose we had data that looked like this. Xj, xk. Correlation is asking, fit the best line and ask about the slope and the tightness of the fit about the line. The best fitting line is flat in this case, which would mean the correlation would be 0. Even though there is very obviously a strong relationship, a strong association between xk and xj. It's just not a linear one. Correlation covariance is an assessment of linear association. If you have data that looks like that, you have no business doing correlation. It's not appropriate because it's not a linear pattern. All right, let me just point forward to where we're going. This is a covariance matrix and a correlation matrix. So I'll talk about that next time. We'll go quickly through this stuff. If you haven't already downloaded R, please do so. Please be reading the R cookbook. I don't think I'm going to do this part. You can look at that if you're interested. So I'm going to finish up topic 1 quickly on Friday so that we can get into topic 2. Topic 2 is our linear algebra background. Okay, so if you're rusty on eigenvalues and eigenvectors, go ahead and start reading topic 2. There were some posts on the discussion boards with Khan Academy and a couple of other online resources that I think are helpful for understanding what we're about to see, linear algebra stuff. Okay, any questions? All right, see you Friday.